in Canada, whenever there's a gathering of people like this, or before a play or a concert, there's always a land acknowledgement. So I felt like I couldn't give this talk without giving a land acknowledgement first because I am here in Toronto. So I am speaking to you from the traditional territory of many Indigenous nations. The area known as Takaranto has been taken care of by the Anishinaabe Nation, the Haudenosaunee Confederacy, and the Huron-Wendat. It is now home to many First Nation, Inuit, and Métis communities. I acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. This territory is the subject of the Dish with One Spoon Wampum Belt Covenant, an agreement to peaceably share and care for the Great Lakes region. Thanks. And so now I want to thank you all for joining me and spending some of your Friday evening with me. And I'm going to tell you about MINERvA. I can't believe we built the whole thing. So this is part 3 of the Fermilab Public Lecture Series, How to Do Big Science. And if you get one thing, if you remember one thing from tonight's talk, it's that in order to do big science, you need a lot of different people with a lot of different skills. So I'm going to show you lots of pictures of those folks and try to explain some of those skills anyway. But before that, I really want to dedicate this song to the teachers of the Fermilab Children's Center. Even though my kids graduated about the time when I started becoming a project manager, I am still very grateful to these folks. They watched a lot of the children of people on MINERvA, people who helped build MINERvA, and so thank you. So what is MINERvA? So MINERvA is the goddess of war and wisdom, but it's also an acronym, and that acronym is the Main Injector Experiment to Study Neutrino A or Neutrino Nucleus Interactions. And so I want to go through and explain for the few of you, for those of you who don't know what all those words mean. First of all, what are neutrinos? So neutrinos are tiny particles. They are they almost have no mass at all. They weigh almost nothing. They have definitely zero charge, but they are created whenever nuclei fuse together, for example, in the sun, or when radioactive nuclei break apart. They're often made, for example, in nuclear reactors. And they were also made very shortly after the Big Bang, when a lot of particles decay, because neutrinos, a lot of particles decay into neutrinos. So how on earth do you study a particle that has no charge and almost never interacts? So first I want to back up and say, well, how do you see particles that are easy to see? So it turns out charged particles are relatively easy to see because they will leave tracks in a lot of different materials. They can ionize materials, they can cause materials to give off light, they'll cause some molecules to shake and give off light. So when you see tracks, you see particles, you're really seeing the footprints that they left behind. And you know from looking at footprints on the beach that sometimes you can tell if you have really very good detector. You can even tell, for example, which of these two folks probably weighed more than the other. So you can even tell by how much, by the footprints that the particles leave behind, the heavy ones from the light ones. You can tell different kinds of particles by those footprints. So how do you see a neutrino if it doesn't have charge? Well, a neutrino can knock into a particle that does have charge and give that particle some energy, or it turns out neutrinos can actually cause a reaction where two charged particles or many charged particles can come out. So neutrinos were first postulated to exist when people were studying radioactive decay. So for example, in nuclear reactors, you have these elements that have a lot more neutrons than protons, and they will undergo some radioactive decay, and that neutron will turn into a proton, but it'll also emit an electron and a neutrino. And it's a particular kind of neutrino. But what Enrico Fermi realized long ago is that you can actually take this neutrino and put it on the other side of the equation. It's a little crazy that you can do that, but he actually calculated what the probability is for a neutrino hitting a neutron and producing a proton and an electron. And when he calculated this, he said, oh my gosh, this is such a rare process. Nobody will ever see it. But he did the calculation, and decades later, people actually saw the neutrino. And so, this is one way that you can see a neutrino, is that nothing, what looks like nothing, turns into two charged particles, for example, a proton and an electron. The only catch is that this process is really rare. So then you might wonder, well, okay, now, this was predicted to happen. We know it happens. Why, what's left? Why do we keep studying neutrino interactions? And one historic example that I can't resist sharing with you, this is probably the most famous neutrino interaction. This picture of this neutrino interaction was blasted all over the place, and it still is. People use it all the time because it's such an important event. What happens is the first time it was ever seen, if you look, the beam of neutrinos is coming from the left, and you see nothing, all of a sudden, boom, something. So what happened is that a neutrino from a beam of neutrinos actually hit an electron that was just sitting there minding its own business in the detector, and that electron shot out in exactly the same direction as the neutrino was to begin with. And so that electron comes out, and we can see from these footprints in this, it's called a bubble chamber detector, that it must have been an electron, and it weighed, it was an electron and it had a negative charge. And this was such a big deal at the time. This was 1973. It was a huge deal because it was a neutrino that cannot make an electron that other way. It's a different kind of neutrino, and it just knocked into an electron. So the fact that this process happened told us not only about neutrinos, it told us about what we call the weak force, or the force that governs radioactive decay in the first place. And so this was a huge thing that had implications far beyond just how neutrinos interact. It had implications about new particles that were only discovered well after this particular event was seen. So in the spirit of this lecture, I cannot help but share with you this photograph of the team, part of the Gargamelle team. So Gargamelle was the experiment that first saw these neutrinos knocking into electrons. And in fact, the people who saw these events first were scanners. They weren't physicists, they were scanners. It was a scanning team. And this is a photograph that includes some of the scanning team from Gargamelle, not the whole team, but certainly these three women are scanners. And the gentleman on the far right with the pipe in this picture is the previous speaker in the public lecture, Jorge Morfin. He was a postdoc on the Gargamelle experiment. So why are we studying neutrino interactions now? We've just seen two different neutrino interactions. Isn't that the end of the story? It's not, turns out. What we're doing now is trying to see inside the nucleus. So we really want to study neutrinos interacting on a nucleus, and we're going to use these interactions to try and probe the nucleus better. And it's like building a digital microscope. So the goal of MINERvA is to collect as many neutrino interactions as we can on a wide range of nuclei. So not just, carbon, for example, or argon, but lots of different kinds of nuclei. And we're going to do it by building a digital microscope so that we don't have to pore over these photographs the way the scanners did. So in order to actually build the detector, it's fine for Fermilab to say, yeah, we approve of this experiment, and that's what you heard about from Jorge. But then you have to get support to actually build the detector. So we asked the Department of Energy, we asked the National Science Foundation, and the way the Department of Energy works is that there are 4 big steps that you need to go through, 4 big reviews. And the motto is, okay, we'll support you, but only if you earn it. So the first step in getting support is to demonstrate that you have a mission need. And I've just explained to you what the mission need is. It's that we need to understand the nucleus better. And we're also providing tools for the next generation of neutrino experiments. So that was the first review. We passed that in about 2006. The next step is preliminary cost and schedule range. And why is your plan to do this science better than any other alternative that you might have thought about? So I want to tell you a little bit about the kinds of things we told the Department of Energy when we were at this stage of review. So the first thing is that MINERvA you can't even appreciate how incredibly efficient this experiment was. So first of all, we used a beam of neutrinos that was built for totally different experiments. So it was originally built for MINOS, and then there's another experiment that came later called NOVA, and we sat in that neutrino beam for both of those 2 experiments. We also used another experiment's detector as part of our way of seeing all the particles, because there are some particles that have a lot of energy, and they would go right through the MINERvA detector we designed, but they would go into this MINOS detector. And so MINOS gracefully shared their data with us, so we didn't have to build another detector to measure the kinds of particles MINOS is very good at measuring. And then finally, we planned to build the detector as quickly as we could, because every day that we didn't take data was another lost opportunity for more data. So we want to get as much data as possible. So that was the plan. And we used to show pictures like this to the Department of Energy. So this is a picture of the MINOS underground hall. And we would say, hey, look, this is the MINOS detector. The front face of it is blue. And there's this big, open, warm, inviting spot, just, dying for a detector to be placed there. And okay, it's 100 meters underground, so it's kind of inconvenient to get to, but it is smack in the middle of the world's most intense neutrino beam. So that was part of it. And we used to show pictures like this where, look, here's a engineering drawing of the detector. It would fit right there so perfectly. So that's what we did. And I'm just going to share with you a few more slides from what we showed at our initial, here's what we want to do, review with the Department of Energy. The active center of this detector is something that can see the footprints very well. So it's a solid scintillator, which is it's plastic doped with the material that gives off light when charged particles go through. But it's segmented, so it's like a digital camera, if you like. And that means that you can see the directions that the particles might be going, and you can try and identify the kinds of particles that got produced in the interaction. And then, because plastic is not very dense, particles don't lose that much energy as they go through it. So we had to put more dense materials outside of that plastic center, and so that was lead and steel. And so the lead is really good at stopping electrons, and the steel is good at stopping other particles. And then remember, the goal of MINERvA is to measure neutrino interactions on lots of different nuclei. So the idea is that we put thin sheets of carbon, iron, and lead interspersed with detector elements, so that if you saw, footprints coming out of some, material, you would know that the neutrino interaction must have started from that material. So we used to joke around that it was kind of like a Cadbury cream egg. We didn't actually have cream eggs on our slides with the Department of Energy, but it was like this chewy center with a crunchy shell. So that was the detector design. And we also were explaining, okay, here's how you put the whole thing together. There's this outer detector, which is steel, but you want to put some readout. You want to be able to measure if a particle has gotten all the way through the steel or just partly. So we had scintillator inside the steel, but then in the middle, we had these rows of scintillator strips. And so if you have strips of scintillator, then if the particle goes through, then you can tell, which strip it hit. So that gives you some information. But if you have two sets of strips at different angles, right, then you can get two measurements or look at it. And so you can do really exactly where did that charged particle go after the neutrino produced it, for example. So that's one of the slides we showed. And then we had, we had an animation about, trying to explain to the Department of Energy, how are we going to put this thing together? So it looks very simple on PowerPoint, trust me. This is, you have this outer detector steel frame, which is assembled from the towers. And then you have to add some hooks, because you have to, of course, support this detector. And then you add these planes of scintillator. And all of these scintillator bars have these fibers that come out of them to transport the light to some device that's going to put it into a digital signal. So then you have the lead rings, so that you can, again, stop electrons. And then you have another scintillator plane. And it's all very straightforward on PowerPoint, right? So this is how you make one module. And then we would explain that, in fact, we're going to make about 120 modules. So we just stack up the modules. And we want to get them as close as we can, but you don't want to crush these fibers, because then you have no signal. Okay, so you stack up all these modules kind of like on a hanging file folder. And then you put a nuclear target in. So you might put like a plane of lead or graphite or iron. And then you put more scintillator planes. So that's the design. And And DOE thought, yeah, that sounds like a good idea. So then we needed to practice. And so one of the first things we did was actually make smaller versions of the detector to see that not only in PowerPoint can you actually assemble something and put it together, but can you really have you really thought of all of the different things that could run into each other? So that's just a picture of an engineer and a graduate student and a postdoc testing that things can be fit together. And then we had to extrude a lot of scintillator. So this is a picture of myself and Anna Pla, who's a chemist, at Fermilab for a long time, and she was developing this extruder. She ran this extruder at Fermilab, which extrudes these scintillator bars, but they were very special bars. They were in the shape of a triangle. And then we nested the triangles together because it turns out you can track the particles better with this setup, because you can see that if a particle goes through, you can compare how much light is in the two different triangles, and that gives you even more information. But anyway, we set up a bunch of these triangles, these long bars, and this is just looking at it from the end, and we tested how much light do you get out, because the more light you get out, the more distinct those footprints are from your particles, and the better you can determine what particle came out of your interaction. So here's a picture of a graduate student doing what we call a vertical slice test, where you try and have just a little bit of every piece of your active, readout. So you have the scintillator and these green fibers, and they are read into another device called a phototube that turns this light signal into an electric signal. So we did tests like that to prove that we could do the physics we wanted to do. And so once we saw that we were getting enough light, it was time to make these enormous planes of scintillator. And so this was all developed at William and Mary, and then Hampton University also started to make a lot of scintillator planes. So you have to nestle together all of these long bars of scintillator, and then it all has to fit in and become this hexagonal thing. But you also need all these green fibers that come out, because that's how you're going to get the light signal. So William and Mary and Hampton are two universities in Virginia that are close enough together that they could, the techniques were developed for these hexagons at William and Mary, and then they shared the technology with folks at Hampton. So those were our two scintillator plane factories. And in fact, you see that, they all fit inside these lab spaces on campus, but at Hampton, they needed more space. So they actually had to rent a warehouse to build their planes, but they did. And here's just a picture of students and an engineer and a physicist, in front of one of their finished planes. And so I can't stress how delicate these fibers are and how important it is to be very careful, because the light is how you get your signal. So you want to make sure that you never break a fiber, and it's very delicate work. So this sort of pays homage to that. So the next thing you have to do is you have to get that light from the side of your detector to the devices that read out the light and turn it into an electronic signal. And the funny story about this is just a photograph of making an optical cable. And we have these clear fibers that transmit the light very well. And everything has to be, you don't want the light to be shared between those fibers. And you don't want the fibers to get any light from the room. So everything has to be light tight. You have to use all this black plastic. But we were going in this underground lab space, and the requirements for flammability are really, really strict if you're that far underground. So one funny thing is that there's actually somebody at Fermilab whose job it is to set things on fire, or at least try to set things on fire. And only if your device passes the fire safety test can you put it underground. So it turns out that the stuff that makes the flame retardant material that you would put into these cables also makes them not light tight. So, we were trying to balance all these competing needs, and we eventually came up with a cocktail that kind of worked. Well, it did work. It just did work, but it took a while. And so here is a clear fiber cable being made. And then of course you don't want to, mix up which fiber went where. So we had to test every single cable and make sure that the order of the fibers didn't get swapped anywhere along the way. So then you have to turn the light into bytes or into digital signals. And so to do that, we used something that we ended up calling a PMT box. PMT is a photomultiplier tube. That's the device itself, the real guts of it, where it has, you give it light and it turns it into the signal, and the rest of it is sort of auxiliary. So these clear fibers here are guiding the light into the front face of a phototube, and the front face of that phototube is shown on the right. This is only 2 inches by 2 inches, but there are 64 little pixels on this phototube, and there are 64 fibers that have to go into those 64 pixels, and that's how we get 64 channels worth of information to a computer, basically. So those are the PMT boxes. And again, we had 2 different universities that assembled these PMT boxes in their lab spaces on campus. And so the 2 universities were Tufts and Rutgers. So these are professors and engineers kind of discussing, sharing notes. It was first developed at Tufts. Here's how we did it. Here's how things fit together. Here's how you weave all the fibers. And folks at Rutgers said, okay, we get it. And so they went back to New Jersey to make boxes. So once you have these, phototubes and you have the electronic signal coming out, then you have to digitize it and it gets read out. And those boards, the electronics that do that, were actually tested in Pittsburgh, so yet somewhere else. So this is a postdoc and a graduate student at the time testing the electronics boards one by one, and there were about, including spares, about 600 boards. So that was plenty to test, and you have to test the gains so that you know how much signal gets out for a certain amount of light that got into your phototube. So then the next step in building this detector is, you remember there were those 6 towers that had to, neatly fit together and make a hexagon. So those all had to be welded. If you buy steel from a vendor, it doesn't come in that hexagonal shape. You have to actually, weld everything together. And the funny thing here is that Fermilab doesn't have a lot of welders on the staff. So we actually had to borrow a welder from Argonne. And so this is the Argonne welder, welding steel, of course. But anyway, he had to go through and make all of these welds in each of the places for this hexagon. But this is only one frame. So once you've built the frame and you have the scintillator, then you have to put it all together. So this is a photograph of a technician from Rochester who is gluing, all of the different pieces into the steel frame. So it's the creamy center in the crunchy shell. He's making sure everything fits and doesn't fall out. So that was great. And but it was not only technicians. We also had graduate students. Actually, this is a master's student in mechanical engineering who was a student at the University of Guanajuato in Mexico. But there were 2 students who came up and stayed a long time at Fermilab to help with making these modules. And so they learned, like, for a mechanical engineering standpoint, about how to do, how to build a detector. And they got to worry about this sort of thing. So, anyway, so we've made now sort of one of everything. And so we have an idea of how much we think it'll cost and how long we think it'll take. So that's the next stage in the Department of Energy review process. Is you say, okay, we know this is what's going to happen when, and here's when we're going to be done. So at that point, this plot is an example of something that we showed. We thought that the thing that would take the longest to do is assemble these PMT boxes, because it turns out, the phototubes were, we couldn't just buy them all in one fell swoop, because, the phototubes cost a lot of money, and we wanted to spread that out and only buy, half of them one year and half of them the next year. So we So that was going to be the thing that determines how long it takes to build this detector, is how quickly we could assemble these PMT boxes. So this is what we showed the Department of Energy, and we said, we are absolutely, we're going to try and be done by October. Our internal schedule says we might be done by October 22nd, but we absolutely promise we're really going to be done by April 1st of 2010. And this is what we thought was going to take us, the rate limiting step, if you like, for getting this detector built. So then we went into sort of mass production mode with everything that I just showed you. So this is a picture of building, we had to build about let's see, 4,000 cables of these clear fiber cables. So these are just, a few dozen of them, but we had to build over 4,000 cables. So that we did, and this was at Fermilab. And then this is now a picture of the folks at Tufts who were assembling these PMT boxes. And so students, engineers, professors, and you can see that they have proudly made 8 boxes, but in fact, we needed about over 500 boxes in total. So, and then of course you might say, well, look, why are these blue? It turns out that at Rutgers, they decided, so blue is the Tufts color, and at Rutgers, they decided, well, we should make the ones at Rutgers red. So anyway, this is the Rutgers team that assembled PMT boxes. Again, students, undergraduates, graduate students, postdoc, professor, and then the folks at Tufts made theirs blue. But those were our box factories. And then, it's not enough to just make 500 boxes. You want to make sure that when you hook them all up together, you can read them out in the way that your data acquisition system expects them to be read out. So we had these tests where we had we call them PMT forest tests, but we lined up several of them. And the way our data acquisition system worked was that the neutrinos only come at very specific times. So in order to be economical, we read out all of the information, all of the data in between when the bursts of neutrinos happened. That way we didn't have to have super fast electronics, but so the whole thing was daisy chained together. So you can see these yellow cables, and we had to make sure that all worked. And so I'm showing here the two students and a postdoc who worked on this, and they actually came up to Fermilab and stayed for a long time, from both Rio and Guanajuato to help us build this detector. So there's a lot of different locations. So I thought I would share some of our shipping routes. It's a little bit, and we did show like maps like this, or at least we described all of these shipping issues, because that's part of building things. You don't want to build it all in one place. And so, for example, you would make the scintillator, extrude the scintillator at Fermilab, then ship it to Virginia, and then the folks at William and Marion Hampton would assemble that into planes. But there were also clear fibers. Those fibers get mirrored and polished and mirrored, and they also get shipped to Virginia. And then they make the planes, and then they ship the planes back to Fermilab. But also those phototubes, those get mailed from Japan. I didn't show that, but they get mailed to James Madison University in Virginia, where they got tested. And then they got shipped to New Jersey and Boston, so that they could, assemble them into these PMT boxes. And then those PMT boxes got shipped back to Fermilab. And then also there were, so anyway, it was a lot of shipping. But in addition to stuff getting shipped, there were also a lot of people who traveled to Fermilab to help build things. So I already mentioned Rio and Guanajuato, but also we had collaborators come from Chile and from Peru to come help us build. It was basically mostly students and a few postdocs who came to help us to build our detector. And of course, we also had students from Rochester and Virginia and New Jersey and Boston, lots of places. So anyway, we eventually managed to get 24 of these modules all stacked together and hooked up to all the electronics. This isn't underground in a neutrino beam. It's still in a building at Fermilab. And we hooked everything up and tried to see what we could measure. And it turns out there are high energy charged particles that are flying around us all the time just because there are protons that hit the atmosphere and cause lots of other high energy particles to get created, and they fly around. And if you're above ground, they're going through you all the time. You just don't feel it. But anyway, we hooked all of this detector up and we thought, okay, well, can we actually see these charged particles? And just to give you a sense of scale, this is a picture of a lot of the collaboration at the time standing in front of the detector. This happens to be Valentine's Day in 2009. But anyway, this is us in front of the detector for scale. And we even had a little trombone concert to celebrate that we got this far along in building this prototype, basically. And sure enough, when we turned on, once we got everything working, we saw these straight lines, which means there's some high energy particle that it's going straight because there's not a magnetic field that's going to bend it. So the fact that you see all these footprints kind of going in a straight line means that we lined everything up the way we were supposed to, and that we never we didn't break any fibers. And so we were all very happy to see that. And we thought, okay, well, let's go underground, because, all this time, there is this fantastically intense neutrino beam just sailing through underground, and we want to get our detector there as soon as we can. So as soon as we saw that our detector worked the way we thought with these charged particles, we took it underground. This is just a slice, a small part of the detector. But here's the very first plane of MINERVA getting installed. And here's that warm, inviting home that I mentioned before. And you can see that there's a rack that's ready to support that first plane. And here are some more collaborators. These are two professors and a postdoc at the time who are furiously looking over the data acquisition and the computer to make sure that, are we really getting all the signals read out as we expect, piece by piece. And sure enough, so we took a whole bunch of data, and the first night, after the first time that we got everything, we thought we had everything turned on, there were a bunch of emails flying around. This is April 1st, 2009, with these modules. Okay, here's the files, everybody. Who can find the first neutrino? And sure enough, a few hours later, somebody sent an email out to the whole collaboration from Duluth, actually, saying, okay, here it is. Look at event 146 in this run. And the reason that we thought, oh, this is a neutrino is because you see nothing, and then you see something. And these colors, this is the neutrino beams coming from the left. You see nothing, and then you see these colors, which means there's light that we did manage to collect, and that's the event. And so this may not look very exciting to all of you, but we were super excited when we saw this. And another way to tell that we really were seeing neutrinos was, as I said, the accelerator will deliver protons on a target and make a bunch of neutrinos, but that bunch of neutrinos happens only every 2 seconds, and the bunch covers 10 millionths of a second. So the neutrinos only come at a very specific time relative to some signal that you get from the accelerator. So we looked at our events as a function of time, and sure enough, this is a plot on a logarithmic scale. We saw hundreds of neutrinos right at exactly at the same time. So that was another big victory, another way that we knew we were seeing neutrinos. So this is with a full prototype. So it was 24 modules in total. And sure enough, here's one of these events where you see nothing coming in from the left, and all of a sudden 2 charged particles popping out. So again, more celebration. And we had a party. And so this is just a photograph of some of the people who were at the party. I can't resist this group of folks down in the lower left. These were the people who polished and mirrored all of these fibers so that we would get the most light possible. And here I am with the deputy project manager, Bob DeMott. And here on the upper right, Karen was head of the technical support, and Jim Kilmer was also as mechanical engineer who was also involved with all of these the hexagonal ring and installation. He was also the project mechanical engineer. Anyway, and then these two children are now out of college and with jobs. So anyway, so we're all very happy that we saw that this detector worked the way we thought it would. But we were looking at how many scintillator planes and how much, how quickly we were building scintillator planes. And it was going more slowly than we thought. And we said, okay, we promise we're going to be done by this certain date. We have to learn how to make things quicker or add another facility to help the factories in Virginia. So they had developed this technique and how to do it, and they were ramping up and making them faster and faster, but still we needed an another plane assembly station to try and speed things up. And so thankfully, Fermilab was able to build another, they had a lot more space at Fermilab than, on these campuses, and they were able to we have students, postdocs, technicians, all helping to make yet more scintillator planes. And you can see, again, it's tricky business. You have all of these very delicate fibers, and you want to try and get as much light as possible out. So we're really racing against time, and this is kind of what things looked like at the beginning of January of 2009. But by the January of the next year, we actually had sped things up and made all of the planes that we wanted to make, and we had managed to ship them all to Fermilab or ship them to the assembly site and put them all in modules. So that was, we were very happy about that. But all was not super awesome because one thing we learned from this data that we took underground is that for a small fraction of our phototubes, these pixels, the pixels on those phototubes were not perfectly aligned with those fibers. And so what that means is you would have light from one bar of scintillator going into two different channels. So it's almost like you would have two footprints for one particle, going along the same place. So like two parallel footprints, and that we couldn't do our science with that. So it was only a few of of the 500 phototubes, there were about 50 of them that had to get realigned. So here are just two of those phototubes getting realigned by Wanda and Janina. And so anyway, we worked through that, but it turns out that was the thing that was our rate limiting step, was realigning and retesting that small fraction of phototubes. And so thankfully, we could still keep installing the rest of the detector and make sure that we put the good phototubes on the detector as we were installing. And then the last ones that we fixed were the last ones to go on the detector. But here's a picture. You can see that the stand is getting filled up, and we're getting more and more detector. So here is a photograph of one of the upstream, these nuclear target regions, because remember, the point of MINERvA is to measure neutrino interactions on different nuclear targets. So this is one target, and if you can see, there are three different materials. This one actually has graphite and iron and lead, all in one target. And then again, if you see that the footprints are leaving from that part of the detector, you know that the neutrino had to have interacted with that particular kind of nucleus. Okay, so now we're at the last step of this whole process, and the last review, this is really the most fun review that you get to have with the Department of Energy. It's okay, we're done. Here's what it really took, and here's the proof that we did what we promised you that we would do. So this is just one event that we showed at our here's what it took review. So again, the neutrino beam's coming from the left, And, I don't know what this is, but it's this, a huge, it must be a very high energy neutrino because it really breaks apart the nucleus and makes all this other stuff. And so this is just one of the millions of neutrino events that we have managed to collect in the meantime. And so that's what we showed. And so of course we had to have another party. And this was so we're all wearing t-shirts that say, MINERVA, I can't believe we built the whole thing. So we had this big party and we gave out all these t-shirts. And I love this picture because actually I think maybe only half of the people in this picture are actually people whose names you'll find on our papers. But there are still, there's administrative assistants, there are technical coordinators, there is safety folks, there's procurement folks, there's professors, there's postdoc students, engineers, technicians. I'm probably forgetting. There's lab administration. There is a chemist in the picture. And anyway, so I'm sure I've forgotten somebody. But anyway, it takes a lot of different skills to build this detector and to build any detector. So even though we had all these people coming to Fermilab to help build the detector, once the detector was built and we started running, we wanted to try and return the favor and visit some of these other places. So once a year, we have collaboration meetings that take place somewhere other than Fermilab. And so we got to Rochester. This is a picture of us in Duluth. We also got to Guanajuato, and we also managed to get to Lima as well. And so it's been a great experience being able to work with people from, with so many different skills from so many different countries. And what I want to leave you with is the fact that we're just sort of one experiment in a long chain of neutrino experiments that are trying to learn more about the universe and the things that we're learning. So just like, in Gargamelle, they found this one interaction that had implications far beyond just neutrino physics. And on MINERVA, we are helping to write the textbook basically on how neutrinos interact in different kinds of nuclei. And that textbook is going to be what the DUNE experiment needs to make sure they can interpret their signals and make sure that when they see a bunch of footprints in their detector, they can do the best job they can translating back to what was the neutrino, what was the energy of the neutrino that caused those charged particles to go through their detector. So what I learned from this whole experience is that, first of all, test everything as early as you can and as often as you can, because what you think will go wrong is not necessarily what goes wrong. It's probably something else. The other thing is that it takes a village, and it's just all different kinds of people that came together to build this detector. And I think those lessons, of course, are being used. This is just some photos, some images from the DUNE experiment. So this picture on the left is actually a picture of a small prototype of the next generation neutrino experiment. And this small prototype feels like it's bigger than my apartment, actually. But anyway, this is a small prototype that's being tested at CERN to make sure that this detector really does what we expect it to do. And then the image on the right is another small prototype of the DUNE, one of the DUNE near detectors. So this is a real data event being, this is real data from a charged particle that's just coming through from the atmosphere, but coming into this near detector prototype. And we're learning how this detector works as early as we can, and we want to test it as often as we can. And another lesson is that it's really nice to have a fantastic photographer nearby, because he can see the art in all this science that we do. So I just want to shout out to Ryder Han, who was a Fermilab staff photographer and took a lot of the pictures for this talk. And thank you very much.